Hi there, so we're going to look at a self-bias arrangement for a NPN transistor. Hopefully this will enable you to understand with a bit more clarity how the NPN transistor works. So what I mean by a self-bias arrangement really is if we have a collector resistor, transistor, emitter resistor, ground, 0 volts. What we need is some bias current to enable this transistor to be switched on. So one method is to connect a base resistor in this way. So one advantage of using this arrangement is the bias voltage comes from this collector point here. So if this collector voltage should drop for some reason, for example if the beta were to change as a result of temperature, then this bias current would also drop, which would in turn switch this or begin to switch this transistor off again, which would then limit the current. Therefore we'd get a bit of temperature stability. So in order to calculate these values for effective biasing, you need to choose what you want to bias this point at initially. So in my case, I want to bias this at, say, half the supply voltage, which I'm going to choose to be 10 volts. So what that would mean is if I want to bias this at half the supply voltage, then we want approximately 5 volts to be dropped across this RC resistor, and we therefore must have approximately 5 volts dropped across this transistor and RE resistor. So this voltage here, this is known as VCE. If we look at a data sheet, NPN transistor, BC547, what we do is we look down, we'll see that the important characteristics that we're interested in, this DC current gain, we'll see for a VCE of 5 volts with IC 2 milliamps, then this will give us the approximate DC current gain. Now this 547B, I know that the approximate gain is the DC gain is about 294 for this particular transistor. So let's go off of these characteristics, and this DC current gain is our starting point. So if we go back here, we've established we're going to have 5 volts. The specification says 2 milliamps. And we're saying that the beta is approximately 294 for this transistor. What we can do is establish our RC resistor as a first choice. So we've got 5 volts and we've got 2 milliamps. 5 divided by 2 milliamps to 500 ohms. Then what we want to do, we've got 2 milliamps and we know that beta is 294, so we do know that IC equals beta IB. Let's make this 1 ohms just to minimize this voltage here and its effect for this 2 milliamps. And we can say that using Kirchhoff's voltage laws, that we have this voltage 10 volts must equal 5 volts plus the voltage across RB plus this approximately 0.7 volts for this diode drop. Based on that, we can work out again an appropriate value for RB. If I go to LTSpice, this is something that I've worked out. So what I've done is I've chosen a preferred value 2K2. I've got a 1 ohm resistor there just to minimize this volt drop here, or keep this current as we want it to be. What I will do is just run this to do some DC analysis. So if we have a look at this current here, yep, this is pretty much where we want it to be, around 2 milliamps. If we take a look at the voltage here, again, yeah, pretty much where we need it to be, 5.4. It's not exact because we're not using 2500. We're also going to get a small loss of voltage across this resistor here, and I've chosen 690k, which I established as the nearest preferred value we wanted to use. So let's have a look at the transient analysis again. I'm putting in a sinusoid at 1 kilohertz. If I run this now, we look at the output. Hey presto, we have a sinusoid, albeit there is some distortion here. So although we've biased this transistor at approximately half VCC, we can see that if we put in this 20 millivolts signal, we are getting a fair amount of gain. Gain of this circuit is going to be approximately 2K2 divided by this combination here. So how do we get rid of this distortion? Well, the thing to remember is, in fact, let's have a look at the distortion. First of all, let's have a look at f of t, and the V out. Yes, we can see there is some second, third, fourth, quite a large amount of distortion there. What we can also do is look at the error log. View error log. And we can see 12.87% distortion, which isn't great THD. So let's try and reduce that. The reason for this distortion is we are taking this point here. If we start at 20 millivolts, and it's a sinusoid. Because we've got a very low value resistor here, we are going to get a very small voltage here. We need to maintain this differential voltage to 0.7 volts in order for this transistor to remain switched on. As this goes negative, this forward bias voltage of this diode is going to get smaller and smaller and smaller, and the transistor's going to switch off. So that's why we see this relatively undeformed positive cycle, but a deformed negative cycle as the transistor begins to switch off. So ways to mitigate that is to, if we want to keep the DC bias voltages the same in terms of current, we could say, okay, well, let's make this 1K5 and let's increase this to 500. Now, this will reduce the gain, or the DC gain of this circuit, but we've got this little capacitor in which should bypass this resistor during the AC, so we'll still get quite a high AC voltage gain through the circuit. So let's try that again. First of all, let's look at the bias point. Let's run that, and let's take a look. Firstly, current. So again, we've not massively changed the current because the sum of these two resistors is approximately 2K, and the bias point, we'd expect possibly that to change. Yeah, so that's gone up slightly. So we've moved away from the 5 volt area, but it's no big deal because we should still be able to, well, that gives us at least, what, 3.3 volts positive swing that we can achieve using this amplifier. And if we look here, this voltage should be higher now. Yeah, so we're seeing that's at 1.2 volts. So let's put some AC signal through, run again. And hey presto, we have pretty much symmetrical swing. We can probably even get away with making this input voltage. Eventually, if we increase this to the point where we violate essentially this difference in 0.7 volts, we're going to see some distortion of this signal eventually. But just for now, we've kind of achieved what we needed to achieve. Have a look at this, quite nice. So we've got a gain of approximately 3, which is what we'd expect. 1K5 and 500. If we look at the FT, We've lost some gain. We've still got a little bit of distortion, but the distortion out of this is down at minus 100 dBs. This is down at minus 140, so it's much better. If we look at the error log, we can see we have vastly reduced the distortion of this particular arrangement.